Hello and welcome to a tutorial on test-driven development basics. In today's video, I want to cover a number of topics and then go into an example. And the first topic I want to talk about is the red-green refactor workflow approach. I consider red-green refactor as a workflow. It's something that I just do. And it's very, very easy when you know how. It's very efficient, and it leaves you with a lot less worrying and a lot more confidence in the changes that you're making to a code base. That is its main benefit, whilst being not a whole heap slower once you've really got the hang of it. It's kind of more haste and less speed as an approach goes. So what is red-green refactor? Red-green refactor refers to three main steps of this workflow. The red step is that we write one failing test. The green step is that we make that one failing test pass. And the refactor step is that we refactor both the test code and the production code, the development that we've just done, basically. An important note, I like to make a commit on the red step, the green step, and the refactor step for each piece of refactoring that I do. And then I will squash down each of those sub-steps as one unit's worth of work, as in this passed one test and got us a little bit further down the goal of implementing that feature that we wanted to implement. There are some best practices that I associate with the red-green refactor workflow. The first is, of course, practice making perfect. I would highly recommend, in the beginning, doing plenty of practice with some very basic katas, just until you get into the habit of writing a test first and the implementation second. It is an unusual way of going about writing code, but it's very, very useful and very, very powerful as a tool in your arsenal when you know how. I would also ensure that you actually do the refactoring step after each passing test. It becomes a very lazy habit to just skip the refactoring step in the aim of progress, but you can end up giving yourself too much refactoring to do in one go. Keeping on top of it is really important. I would also say to reduce the number of red-green refactor loops by making obvious refactors in time, right? Just in time. When you spot something really simple, just do it. Don't spend another loop or wait until the refactor step to then refactor it. Just do it, right? If the implementation is simple enough, and you'll see examples of this as we do plenty of this here in this series, right? Ensure there is only one failing test. Now, this is a really important one, especially in the beginning. You can bend these rules when you get a little bit more experience with it, but ensuring there's only one failing test keeps the development focused, and you're not trying to play whack-a-mole, basically, with multiple tests to ensure they all pass. Just stick to the next thing and progress it piece by piece. Iteratively, basically. It's an iterative development approach. And again, just to reiterate my point about the obvious refactor, but you want the simplest implementation to be written. But again, if you can see an obvious refactor, do it. Don't necessarily have to write a fake, then triangulate, and then come up with a proper solution. If you can spot a proper solution, just do it. And then you can always use that test to refactor it and refine it later. The next part of the test-driven picture is types of testing. As a developer, developing unit tests for our test-driven development approach, we have three main tools in our arsenal: response tests, side effect tests, and interaction tests. Response testing is the typical unit test example you'll see around the internet. It is some parameters in, some manipulation of those parameters, some response returned. And in this example, we have an add function with two numbers going in that get added together and returned out of the function here in this uint. And we can, of course, write a test for that. I want you to note the name, adder should. Adder should implies what should the adder do? Well, maybe an adder should add two numbers. Whoops. Maybe an adder should add two numbers. And we can provide that in our given step. Our test should follow a or triple A or a given when then sequence of steps. We provide what it's going to do in the when step, what it needs in the given step, and what we are testing against in the then step. The adder will take the first number, which is an expected value, very important. Our second number, which is an expected value, which is very important as well. And return a result, which is our actual result. And we can compare that against a known expected result. Another important point we want to address whilst we're here, we do not want indentation within our tests. We don't want if statements, we don't want for loops. It should just be a straight line all the way down with one level of indentation for the method, test method itself. And that is it. You might also want to provide a theory with multiple lines to test variation and allow you to triangulate some sort of algorithm, etc., etc. And you can, of course, therefore pass the first number, second number, and expected result into a parameter list, into the parameters like so. And that would be the given step with your when step and then step doing the same as before. Response testing can also include exceptions. You might have not thought of that, but that is a thing that it can do. For example, this product makes a purchase. This shop makes a purchase and returns a product. And maybe there's some condition that throws in some sort of exception that we could define here. You can see in our test, when we purchase a product, the shop should purchase products. When we create our shop and we run the specific version of our method, we would expect it to return some sort of exception. So we can test that response as well. Side effect testing. Sometimes when we invoke behavior in our code, it can generate side effects, which can also be tested against known values. In an example here, we have this driver model, and we have a name and penalty points as properties. I wrote this quite a while ago. We can update the license information here as a public exposed method. We provide a name in and penalty points. This is effectively a setter, but you could imagine such a case where you would have some other manipulations and so on, maybe some validation of the name or validation of the penalty points. And then you can pass this information into this method in a test and check against the result, basically, that you would expect, which would come from the properties of name and penalty points that are assigned against our known name and known penalty points here. Last but not least, we have interaction testing. Now this requires a short explanation of what testables are. Well, I have such a slide available for us to look at. Testables are objects or code constructs that are used in software testing to simulate the behavior of real objects or dependencies that are tested that a tested object interacts with. Another way of putting it, basically, you want to keep your test a unit test, as in you want one unit and that unit would be usually the class of the should. So adder should, you would be testing the unit of adder. Anything that adder consumes should be a test double, and you would test the interactions of the adder unit with its collaborators, such as an adder controller, some sort of adder service, etc., etc. You have different types of test double: mocks, stubs, fakes, dummies, and spies. Mocks basically record the interactions, as in anything that's invoked on the collaborator. Spies are more specific. They want to know specifically how many times a method was called, whether it was called more times than you expected, that sort of thing. Stubs provide a predetermined response to a function call, and again allow for testing interactions where maybe a false would lead to a different path, or a true leading to a different path within a method. So that's where they're used. Dummies are simply to fill out a parameter list, that's all. And fakes are a simple implementation that would consume an interface and provide things like an in-memory database, or a web server, or things like that for testing purposes, so that you're not hitting some real or test database, and it would provide more speed as a result. Okay, now that we've explained what test doubles are, interaction testing uses those test doubles and basically writes tests. It's testing those interactions of the collaborator with our unit. So this is the shop service, which is our unit, and our collaborator is the shop controller. Note that it's an abstraction, so you can actually test basically the interface and provide a real version of the shop controller later. You pop the shop controller in somewhere. This is called dependency injection. You can either pop it into the constructor, or you could pop it into the method. If you don't, you won't have access to the reference and your test won't work. From here, you can write tests. So, for example, this displays sales. We create the shopping controller as a test double. We provide a mock of display sales. Whoops. And we can then inject our shopping controller into the constructor argument, run shopping services to display sales, and verify shopping controller calls its display sales and nothing else was called. If we have a look, you can see our shopping controller has a concept of display sales, and our shopping service has display sales as well, this concept of display sales, which uses the collaborator of shopping controller dot display sales. So we're testing that this ran. You can also see an example where we've used a stub, and this also uses some sequencing as well, and we're testing that purchase returns a product, and then we're testing, which we've created a dummy for, and we're testing that the shopping controller sells a product and returns 1. And in such a case where it would return 1, that's all the calls that we would expect. And we can verify everything went the way we expected when we call replace and sell, replace stock and sell product. In this other example, we have one where the total sales are more than 5. So we can see here we return 6, and as a result we'd expect to calculate remaining stock. This is just an example, And then we can verify all of those calls were made when we call this method. So this is some examples of how you could use interaction testing to test how collaborators interact with your unit. And it forms the outside loop, which we will cover in another episode of an outside in to inside out tutorial, basically, using probably the banking kata. Okay, that is enough of me waffling. You can see here that we have a branch called FizzBuzz Demo, and we're going to get into a practical example. I'm using C# for this Kata demo. I'm using .NET 9 specifically, which dates this video. Probably be 3-4 versions out by the time someone watches this, but never mind. Past that. Treat warnings as errors I have on true on both projects. I'm using XUnit as my test runner, and FizzBuzz project reference obviously in my test project, and for my actual production code project, same sort of idea, .NET 9, treat errors, warnings as errors, and there's obviously an executable output. Let's read what the FizzBuzz Kata is about so we know what we're doing before we do anything. Always a good idea. So, I always make some sort of joke. Basically, the aim of the FizzBuzz Kata is to provide 3 main functionalities, or was it 4 main functionalities? 4 main functionalities. If a number is a multiple of 3, we want to return the string of fizz. If the number is a multiple of 5 even, we want to return the string of buzz. If the number is a multiple of both 3 and 5, we want to return the string FizzBuzz. This would be the interface that we will use, and we are not going to be changing this interface. And then basically we've got to make this work. So it's going to look something like 1, 2 fizz, 4 buzz, fizz, 7, 8 fizz buzz, not fizz buzz, but fizz then buzz, 11 fizz, 13, 14 fizz buzz. Right, very good. We can refer back to this document anytime we like as well whilst we're doing this kata. It's open book, so to speak, so no pressure. It's all about learning the approach of test-driven development. I'm also going to make notes of when I make a commit. So again, you can follow along at home and follow by my example. First things first, like Blue Peter, here is one I did earlier. We have the iFizzBuzz interface, string, convert, uint, and the number. Just like in our README. Well, I hope, well, very least similar to what was in our README. Next thing, I'm going to make a test class. Now that might alarm some of you. Some of you might go and create FizzBuzz first, but we're going to create the test class first. So let's do that. FizzBuzz, and remember, we're going to use should, because we want to imply functionality. Let's spin this up. So namespace and public, and we want class. And before we start anything, let's make sure we have some running tests. That everything compiles, all is hunky-dory. What we don't want is a state where we've started to make changes to the code and we don't know what the errors are. You can see we have 0 failing, 0 succeeding, 0 everything, right? But at least everything compiled and all as well. Okay. I'm going to use a macro called fact. It will generate me a test. Import xUnit. And then I'm going to give my test a reasonable name, a doing description of what FizzBuzz is doing, right? A doing word. Whatever a doing word's called in English, I've forgotten. I think it's an adjective, isn't it? Convert, right? FizzBuzz should convert number to string. You could maybe put, or you could just have convert, right? Now, in this case, we're going to keep the test really simple, and I'm just going to show you it as you might go through, but I'll describe throughout where I might, do the obvious refactors. So the first obvious refactor, first thing I'm going to do rather is FizzBuzz equals, and then we're going to do this FizzBuzz, which is going to be. So we have this interface. Oops, sorry, I meant to hit the home key there. We have this interface, and we're describing the interface here. So this is our variable, and we haven't got a concrete yet of our abstraction of FizzBuzz. So let's create that. But let's create that using our IDE. Let's not worry about creating it by hand and all of that sort of stuff. Use your IDE, use your IDE's power. And again, we can implement the interface here. It's done all of that for us. Now, okay, you've got the accessor wrong. We can just change that for ourselves. If we can type. And we have our method that isn't implemented. So let's implement some sort of step. Is it a uint we want? And what I like to do for this is define the when step, because it allows us to work out what we need. And we can see if we hover over convert, we need a uint. Okay, so let's add a uint to our step, our given step. So, for example, we can define number, and we can have that equal to 1, more than reasonable, right? And we can pop number in to here, and on our then step, we can assert what that would be equal to, because convert returns a string. So now we can have a string here of our, what we call it, results, and we can test against a string of expected result, which would be 1, right? So we can do expected followed by actual result. This is a valid test. We have 3 steps. Our given steps all based on known values. There are no method calls going on in our given step. That would be a smell of our test. We define our FizzBuzz object, our unit, and then we run a method that FizzBuzz has with our number, produce an actual result and compare it to an expected result. So this is a valid response test. Let's commit that. Some people like to commit on a green test and then do their refactoring. I like to commit on our newly defined red test. At least if you screw up in the green step, you have a valid test you can fall back to and you can have another go. Let's run the test, see if we get an expected result. We don't make assumptions when we do test-driven development. The expected result I'm going to assume, without looking at my screen, is a not implemented exception. I'm now going to see if that's what we got. And if I read down here, the method is not implemented, stack trace, blah, 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 blah. But the point is, somewhere around the place should tell me it threw a system not implemented exception, right? That was the description of what it is, that exception is. That's fine, because that's what I assumed, but we don't make assumptions. It's kind of difficult to explain. We're not computers. We don't know what's going to happen when we write our code, right? We don't think like computers, and we've just got to be aware of that at all points. So let's do the simplest implementation. And I wouldn't normally do this. This is one of the quote simplest implementations you could do. But we know that that's a fake result, and we don't need to be this pedantic when doing test-driven development. This is also valid, in my view, for a first loop of red-green refactor. It's still going to give us the green result, but we don't then need to do another test, another loop, check that, like, you know, it went green because we put 2 in, and then 3 we have fizz, and then 4 is fine, and 5, you know, we don't have to put all these cases we know are going to just return the string number in. We can do it one time, right? One less, or two less loops to prove we did it, right? Okay, less statically written, let's say. Again, I'm going to run the test. I'm going to run the test first. We don't assume it's going to pass, but it did pass. That's good. We're now confident that when we put 1 in, it will return 1 as we expect. So we can commit this step. But we know there are some other behaviors that we're expecting. So let's go and have a look, obviously, if there are any refactors we can do. Well, at the moment, not really. So let's see about maybe the next test. Well, to do the next test, we might want to consider a theory. So this could be part of our refactoring step, because we're going to refactor the code, because we realize, okay, for the next test, we're going to need something a bit more like this. And we can do uint, isn't it? Uint number. And we can do a string of results, expected result even. And we can get rid of these. And now we can run the test. So this is effectively our refactor step. We don't want to derive new behavior if we're refactoring our code. So that's our refactor step. So now if we look at my very lazily written commit messages, we have basically our red test, our pass test, and our refactoring step. And if I was to, do this really properly, and all of my commit messages and stuff, I would obviously write a descriptive name for each part, that this is test 1, or I'm doing basically the number return for the FizzBuzz conversion, and this is the red part, the green part, and the refactored part, and all of that sort of stuff. You can name this as a feature, everyone's different for how they want to do their Git workflows. But principally you can see what I'm going for here. Okay, the next one we can box off. We know 2 should do that. We know 4 should do that. And that gives us a bit of triangulation. Proves that we're actually using the real number to string rather than returning some fake result. So we can just test that, even though it doesn't drive out new behavior. I do like the assurance of running 3 tests to test one piece of functionality, just to make sure it works with a couple of different parameters. So I'm going to commit that. That's another little refactor I've just decided to do. And you can do multiple commits for the refactoring step. And I have 3 passing tests. We now need to challenge the behavior. And the challenge to our behavior would be fizz or the buzz, right? So it doesn't matter which way around you do it. I can't remember what one does what, so I'm just going to have to reread the requirements. 3 is fizz, 5 is buzz, and then we've got FizzBuzz. Okay, so 3 would produce fizz, and 5, I'm just going to do this, would be buzz, and 15 was FizzBuzz. Now remember, we don't want multiple failing tests, so you can skeleton out where you want to go and just leave the new tests commented out. Okay, so let's run our test. And we can see that it will fail because we haven't defined this behavior yet. It's expecting fizz, and we actually got back 3. So let's commit this because it's a valid test. And we have 1 failing, which is always good. And then let's go to our implementation and put in a condition. Right? There's a condition if number equals 3, then return this. And this works, right? In principle, let's just ensure that's the case. And we can commit that. And it is the simplest implementation, but yet again, it is a static response. And if the only case was 3, then that would be fine. But we know that such cases as 6 and 9 exist. If we look at our README, we can prove this to be the case. 4, 5, 6, 8, 7, 8, 9, right? Fizz, fizz, fizz. So we need to prove that. These 2 tests challenge that behavior and ensure that we're going to make a proper result. You could do it this way, you know, of course, and take it 1 step at a time. There's no harm in that. But again, we're wanting to triangulate. I would say 3 tests to test this is perfectly valid. And a way we can do this is number modulus 3 equals 0. Modulus basically returns a 0 if it's a multiple, and I think it's a 1 if it's not a multiple. I think that's the case. Or, sorry, not a 1. It returns the remainder if it's not a multiple. So it's basically how much remainder there is. So 0 would be 0 remainder, and therefore it would be valid, right? So if we run .NET-test, you would hope we'd have 6 passing tests, but we're not going to make assumptions. We do. That's great. Let's commit it. Now we can move on to 5. Now, we have an established pattern, so we don't need to waste time here. We can actually do 3 tests at once and stand a reasonable chance of passing them all. So 5, 10, 20, I believe, are all valid. I don't think 3 is a multiple of 20. 10 is certainly valid, so that's at least 2 options. That. So yeah, so that's 3 valid buzz cases. And we can just simply, well, we can run this. See that we have 3 failing tests, you'd hope. 3 failing tests, commit it. And we can make those 3 failing tests pass. Number modulus 5 equals 0. Return buzz. What's all the buzz about? .NET test. And you can see we now have 9 passing tests, and we've proven it works with 3 valid cases from 6 valid cases and 3 failing cases. So you can see how sometimes you can bend the rules, but you need to have some established pattern or confidence that you can make all of it pass in one loop. Otherwise, you'll have to revert back to your previous commit, and you have to hope you've done that. And that requires discipline, and as you're learning this process, that's pretty tricky. So keep all of this in mind at the same time, because there's so much mental task loading when it's a new concept. Now we can do refactoring steps. We can include an else statement here, and that's about all that's reasonable for us to do. So we can just run our tests again, just to ensure that that refactoring step worked as we expected. And it did. And I've just committed that refactoring step. So the final set of tests we are going to run is the FizzBuzz, which is basically any multiples of 3 and 5. So for this, again, we have an established pattern. We know that we can do 15, 30, 45, 60, so on and so forth, if you really wanted to. And we're going to have 3 failing tests, and we know that to write the if condition and all that. But let's run through the red-green refactors, just because in some cases you think it's obvious, but if you don't drive it from the test, you can still make mistakes. And I'll show you an example of where you can make a mistake with this. So, .NET test. We have 3 failing tests with our established pattern, which is fine because we're bending the rules slightly. We're getting buzz back where we should be getting FizzBuzz for 2 of them, all 3 of them. So let's commit. And our valid failing test, right? And then let's write an implementation that we think is going to pass the test. Where's my percent sign? There it is. So we're going to follow that pattern that we came up with, because it's pretty valid for the others, right? And we can return FizzBuzz, which is exactly what we were expecting. And again, we don't make assumptions, and we run our tests, and we get 3 failing tests, right? But surely that should have passed, right, guys? Because we put in our pattern, we put in our implementation. Why would it possibly do this? Well, the reason in this case is because we would want that at the top. Let's do what I would do in such a situation. Say this was a harder example. I would do a git reset hard. Now this has put us back a step. This has put us right back to our 15, 30, 45, three failing tests state that we had before. So let's run our tests. And we have 3 failing tests as we expect. again, we want to run our tests. We are in a known state. Even we obviously would hope to be green if you've done a complete feature, but in this case we're driving out a new feature, so it's fine, right? We expect this. Let's have another go at it. Where could we put this to make it pass? Well, what about if we put it up here? Right? Get this one out of the way first, and maybe it will work, right? Maybe. I don't know. I'm making an assumption that this is the behavior that we're intending or wanting. Let's put another else here. And let's give this a run. Let's see if this gives us what we want. Oh, there you go. Right, so we now have 12 passing tests, exactly what we want. And we don't need to do any more, really. We can commit this, step. And if we do our log, we can see, we roughly have, failing, passing, refactor, failing, passing, refactor, roughly speaking, for each of our steps, our red, our green, and our refactor. So let's have a look, see if there's any refactoring that we can do now that we've completed the kata, right? We've completed all the requirements for this kata. I think the first thing we can obviously do, let's move this file out, this implementation out, to its own file. That would make a lot of sense to me. For that, we can open up our Explorer, and we can add FizzBuzz CS here, paste, and wrap that up in a nice little neat namespace. Badoop, 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 and badoop. And FizzBuzz is in the same namespace now. So everything is happy here, and then I just need to go to here and import, I think, using FizzBuzz. FizzBuzz is a namespace. Oh, okay, let's call it FizzBuzz Kata and FizzBuzz Kata. And then in theory, everything should be fine. I can just use the namespace like so, remove the old one, and run my tests. Namespaces being the same as class names is a classic. And I still have 12 passing tests. Are there any other refactors I could make? Well, the test, if I was to have more tests than just convert, then maybe FizzBuzz. Is there any exceptions I want to consider? Maybe zero? Maybe zero could just throw an exception or something like that. Possibly, but I think for the purposes of this video, we can conclude, right? We've done the kata. There was no, if you pass 0 in, I expect you to fail. It started from 1 to 15, so we've met the requirement. And yeah, hopefully you guys watching learn how to approach the red-green refactor approach, where I commit, where it makes sense to commit. Obviously we just covered a response test here, and there are other types that I'll cover in later videos. And the given when then test structure, or the arrange, act, assert test structure, expecting your results on a known value. You don't want to be having method calls to give you your known values in the given step. So that's really important. And then the result, of course, being the response that we're testing, and then setting it up with our unit, our single unit of the FizzBuzz. So yeah, I think that covers just about everything I wanted to say in this video, and thank you very much for watching.